Gaston was the first person from the Central African Republic to get a PhD in mathematics. It came in 1980 at the University of Montreal. His thesis under Samuel Zeidman was in French, one of his several native languages. It dealt with periodic functions, almost periodic functions, and almost automorphic functions. The first two of those areas were highly respected areas, but almost automorphy was a more tentative area. The functions and their applications were hard to construct, despite the initial efforts by John von Neumann and Sal Bachner in this area. And it was hard to find concrete examples and applications. After his PhD, Gaston returned to the Central African Republic and quickly became a full professor, a dean, a teacher of graduate students, creator of the graduate program, then Secretary of State of the Central African Republic. And as such, he addressed the United Nations. He dined at the homes of dictators and other kinder heads of states. A coup led to the demise of the president's cabinet in the CAR, and Gaston was spared because his wife was related to the general who became the next president. So Gaston remained a mathematics professor, then got a Fulbright scholarship, went to Berkeley for a year to work with Toshio Kato, and he reinvigorated his research life. But he loved periodic, almost and almost automorphic functions, and he declined to abandon them. He did enough new and original research in these areas, especially in the latter area, that almost automorphy became very popular and much used and much applied. His excellent 2005 monograph was updated and published recently by Springer. His passion for research and in these special areas was contagious. And he converted many serious mathematicians to becoming experts in these areas themselves. An economic crisis in the CAR led him to leave and come to the United States. He worked for a while at Buffalo, then took his present job at Morgan State. There he became highly influential and got a huge National Science Foundation grant to create the PhD program in mathematics at Morgan that Gaston heads up. He continues to be very creative and very influential. He is one of the most interesting and remarkable people I have ever met. The title of his talk today is An Invitation to Periodicity.
I believe you're muted, Gaston.
Some physical and biological motivations. We will discuss everything here from the point of view of differential equations. We will also look at a second order, semilinear, elliptic, almost periodic equations. We will show that this equation has no almost periodic solutions, but many almost automorphic solutions and many almost periodic functions in the sense of Besicovitch in the envelope of the equations. Then we will apply the result to study the almost periodically forced pendulum. And at the end, we will draw some conclusion to this talk. Okay, so everyone knows that a periodic phenomena is the one that repeats itself so often, and the period of the periodic phenomena is actually the time required to complete one cycle of the phenomena. Examples of periodic phenomena include the rocking chair, the heartbeat, and the pendulum. Periodic sequences are known in mathematics. Here are some examples of periodic sequences with their respective periods. All civilizations, from the ancient ones till now, are familiar with periodic patterns. Here we give an example of a tribal African fabric pattern from Tanzania, from Zanzibar. Now, in physics, a periodic motion is the one that repeats in equal intervals of time. Examples: water wave, Earth orbit, with period 1 year roughly, and we will explain the meaning of roughly later on. The frequency, we will talk about what is the frequency of a periodic motion later on. The frequency of Earth orbit is 1 year, 1 orbit per year. Also, example of periodic motion, the bouncing balls. A simple harmonic motion is a special case of periodic motion. And the example are the rocking chair, for instance. And counterexample include bouncing balls, orbit, or the Earth. So there are two important concepts when we study periodic phenomena. These are the concept of wave period and wave frequency. So we will present this short video to talk about it.
Hi, it's Mr. Anderson, and this is AP Physics Essentials, video 104. It's on wave period and frequency. Period is the time between oscillations in a wave, and frequency is going to be how many oscillation or waves do we have per unit time. Now, it's sometimes easy to confuse frequency with the velocity of the wave, and so we're not even going to start with waves. We're just going to start with some flashing lights. And so the light on the left is flashing. Try to figure out the period. How much time is there between each flash? And the right answer is there's 1 second. And so the period, or capital T, is 1 second. There's a flash every 1 second. That's the period. What's the frequency then? Well, we're having the flashes, and so it's how many flashes we have per second. And since we have 1 flash every second, our frequency is 1 flash per 1 second. Now, the units for that is going to be in hertz. And so our frequency is 1 hertz. Now let's look at the other light. And so it's flashing as well. Try to just figure out what the period is. You can see it's slower. And so the period in this case is going to be 2 seconds. So it's taking twice as long between each of the flashes. So what's going to happen to the frequency? So now we've got 1 flash per 2 seconds, and so what's going to be the frequency? It's going to be 0.5 hertz. And so period and frequency will always be the reciprocal of each other. Once you know period, 1 divided by period is going to tell you the frequency and vice versa. And so waves transfer energy through oscillations. The wave period is going to be the time between the waves, and then the wave frequency is going to be a wave or a set number of waves per unit time. Now we measure period in seconds, and then we're going to measure wave frequency in hertz, which is the number of waves per unit time. Now, if you're ever looking at a wave diagram like this, the first thing you want to do is figure out what are my axes labeled. And so the position is changing here, but this is over time. Now, you could also have wave diagrams where it's position here and position here. But since we have time on the x-axis, if I want to figure out what the period is, I simply measure the distance between waves. And so I find 1 wavelength. So 1 oscillation, and then the distance between the two is going to be the period, or it's going to be the time. If I wanted to figure out the frequency, then it's simply the reciprocal of that. And so let's do a little simulation. This is a PHET simulation. What I'm going to do is generate some waves. And so those waves are moving from left to right. And so this is going to show us the position, but it's going to have a certain frequency and therefore a certain period. Now, a way to see that is to slow it down. Since we're looking at a position of the wave over here, I've also added a clock. And so we can keep track of that time. And so we're going to create 1 wave. And so I'm going to stop it after we go through 1 oscillation. And so what's going to be our period? Well, we've got the 1 wave here, but what's the period? It's the time. It's simply 0.67 seconds. And so that's the time distance between waves. We're just about to start another wave. Now, if I want to figure out frequency using this simulation, what I could do is just let that clock run until it gets to 1 second. So I've stopped it here, so that's 1 second. And so how many waves do you see on the screen? Well, I see 1.5 waves. And so our frequency is going to be 1.5 hertz. Now, we could have done it just by looking at the simulation, doing some experimentation, or we could just do it mathematically. If we want to convert from 0.67 seconds into frequency, all you do is we would take that period that we calculated, 0.67 seconds, we take 1 divided by 0.67 seconds, and we'll get 1.5 hertz. Let's say you're given a problem and you want to solve what the period and the frequency are. The first thing you want to do is look at your axes. And so we got meters here, and then we've got time. And so if I want to figure out the period, remember I just find one wavelength. And so I could say right here is the top of one, and we go back to another top. So this one's at 25 seconds, this one's at 45 seconds. So what's my period going to be? It's going to simply be 20 seconds. If I want to figure out what the frequency is then, what's the easiest way to do that? Well, once I have my period at 20 seconds, I simply take 1 divided by the period, and I'm going to get a frequency of 0.05 hertz. And so did you learn to use a graphical representation of position versus time to calculate the period and the frequency? I hope so, and I hope that was helpful.
Okay, thank you. Now let's get back to mathematics and recall the definition of a periodic function. It's any functions that satisfy this equation for any t. When we have the minus sign here, in this case, we say that the function is entire periodic. Of course, a t entire periodic function is 2t periodic. Now, let's look at this very simple problem in calculus to try to understand the transition to a differential equation. So we consider the primitive of a periodic and continuous function with period, say, 2 pi. Example, if the function is cosine x, then the primitive is sine x plus c. It is also 2 pi periodic as f. And if g of x is 1, which is also 2 pi periodic, the primitive is x plus c, is not 2 pi periodic as small g. So, generally speaking, if f is a t periodic and continuous function, then when is the primitive capital F also t periodic? We have two cases. One is the special case here where the average of the function is equal to 0. In this case, if we consider the primitive capital F, then using some change of variable, we can show that f of t plus capital T is equal to f of t, meaning that capital F, the primitive, is also t periodic. The general case is when we assume that a is not 0. In this case, we make a change of the function. We put small g is equal to f of t minus a. Obviously, small g is t periodic and has 0 average. The primitive is equal to f of t minus at. Of course, based on the special case, because g has a 0 average, then capital G is also capital T periodic. So we come up with this representation of capital F, where we know that this time capital G is continuous and T periodic. So the answer for capital F to be T periodic is either A equal to 0, the average, or capital F is bounded on the non-negative semi-axis of real numbers. In conclusion, we can say that there is a relation between the boundedness of the primitive capital F and its periodicity. Moreover, the fact that the average is equal to 0 is related to the fact that 0 is not a Fourier exponent of capital F. This implies that the primitive of f relates to the Fourier exponent of mol f. So how can we, generalize this, let's say, result from the point of view of ODE and apply it to study the asymptotic behavior of solutions of ODE? First, we have the so-called Masera theorem. In a finite dimensional space, that's this equation where A of t and f of t are both continuous and t periodic. A simple example of such a problem is the following differential equations, where the forcing term here is pi periodic, and the general solution, as we know, is equal to that function. Now, the only pi periodic solution to this equation is this function, right? And we notice also that all solutions are in fact bounded. So Masera's proof this very beautiful theorem. He said that equation 1 have a t periodic solution if and only if it has a solution that is bounded on the non-negative semi-axis of real numbers. This is a very beautiful theorem indeed, because it's we obtain the result under really minimal conditions. We don't have enough time to present the proof here. It's an elementary proof, very beautiful, that you can find in this monograph. Now, about the uniqueness of that equation 1. Then the condition in the case where A of t does not depend on t is that the spectrum of the operator A does not intersect this set. Okay, that's the condition for the equation to have a unique t periodic solution. You can see here the expression of the frequency of the forcing term f, right? As we saw during the video watch. We will denote by a p sub omega of x the set of all continuous omega periodic functions. The first generalization of the concept of periodicity was given in 1941 by Maurice Fréchet. He said that a function f from r plus 2x is said to be asymptotically omega periodic if it has this decomposition where g is a periodic functions, omega periodic function, and h a continuous function that goes to 0 at infinity. Omega is a given positive number. We will denote by ap omega x the set of all such functions, and notice that actually this set is the direct sum of the set of omega periodic functions and the set of functions that go to 0 at infinity. An example of such functions is given by this one with its graph. A second generalization of the concept of periodicity was given by Henriquez, Pierry, and Talbot in 2008. It's the concept of S asymptotically omega periodic function. So a function from R plus to X, any Banach space, is said to be S asymptotically omega periodic if this expression holds. In this case, omega is called an asymptotic period of f, and we will denote by SAP omega x, the set of all such functions. And we note that it contains strictly the set of asymptotically omega periodic functions. The proof is given by at least this example, and you can find it in the paper, pioneering paper by Henriquez. In physics, our colleagues, are very familiar with what they call a block periodicity. It's actually the functions that have this form here. These are actually the solution of equation of propagation of heat or waves in solid state physics, where C is the wave function, R denotes the position, K is the wave vector, and phi is a periodic function. So this concept was not very known by mathematicians, and recently in 2014, we gave a formal definition of such types of functions. So we call any function from Rn to X, we call them pk periodic or block periodic if they satisfy this equation, okay, for any t. K will be called the block wave vector or flow k exponent of f. Now, it's easy to see that if f is pk periodic, with pk is equal to 2 pi, then f is simply p periodic. And if pk is pi, then f is entire periodic. Recently, we have published this book, which contains the recent development of the concept of block periodic functions, and I invite the reader to take a look if you are interested. Another concept of periodicity is the one of which we call omega C periodic functions. Let's first give here two motivations. One is the Matthew equations, okay, which is used to model several phenomena, including the stability of railroads as trains drive over them, and seasonally forced populations dynamics. This equation actually has solution under this form, where omega is a positive number and C a complex number, non-zero, of course. The second motivation is from the Schrödinger wave equation, whose solutions are also given under this form, where U sub k is periodic. From these two motivations, Alvarez, Gomez, and Pinto in 2018 define a omega C periodic function to be any function that satisfies this equation, okay, where omega is positive and C a complex number. And in this case, omega is called a C period of F. Clearly, if C is equal to 1, F is periodic. If C is equal to -1, F is entire periodic. And if C is a general general complex number, then F is a block periodic function. So omega C periodic functions include periodic, entire periodic, and also block periodic functions. So the very interesting concept of general than periodicity is the one called almost periodicity. We know, in fact, most of natural and biological periodic phenomena, which we call periodic, are in fact almost periodic, meaning that they are periodic up to epsilon. Example: the seasonal harvest, the heartbeat, the harmonic oscillation if in evolutionary processes, the biological clock, and of course, quasi-crystals. If you read this very interesting paper by Mayer. He presented quasi-crystal as very natural, beautiful example of almost periodic phenomena. Here also we have, an almost periodic pattern, a very beautiful one. And that one also, another almost periodic pattern. Now, let's give also another example of almost periodic phenomena. It's the one of biological clock. So I invite you to watch this.
Although you don't hear it tick, your body has its own clock. We all experience different levels of sleepiness and alertness throughout the day. Staying up late is not an easy task for some people. Have you ever wondered what causes these patterns? Sleep is regulated by two body systems, sleep or wake homeostasis and the circadian biological clock. In this video, we are going to see how the biological clock works. Circadian rhythms are physical, mental and behavioral changes that follow a roughly 24-hour cycle. It regulates the timing of processes like eating, sleeping and temperature. Our biological clocks drive our circadian rhythms. About 20,000 nerve cells make up our master clock, a part of our brain called the suprachiasmatic nucleus. This structure, which sits inside an area called the hypothalamus, controls your circadian rhythms. The most significant signal is the light. Your body is wired to sleep when it's dark and stay awake when it's bright outside. Nerves directly link your eyes and your body's master clock. When daylight fades, your eyes signal your brain to make more melatonin, a hormone that makes you feel sleepy. And when the sun rises again, the signal tells the brain to turn down the melatonin. Biological clocks regulate the timing of periods of sleepiness and wakefulness throughout the day. The circadian rhythm dips and rises at different times of the day. Adults normally experience the strongest sleep drive between 2 to 4 a.m. and in the afternoon between 1 to 3 p.m. Although there is some variation depending on whether you are a morning person or an evening person. The sleepiness we experience during these circadian dips will be less intense if we have had sufficient sleep and more intense when we are sleep deprived. The circadian rhythm also causes us to feel more alert at certain points of the day, even if we have been awake for hours. Biological clocks are fundamental to the functioning of life and the organization and coordination of behavior. Every tissue and organ in your body operates according to biological rhythms. The circadian rhythms generated by our internal biological clocks vary from individual to individual. Most clocks run slightly longer than 24 hours, while some run slightly shorter. This is why some people are early birds and some are night owls. That's all for this video. Let's meet again with some more amazing insights. Till then, don't forget to like, comment and subscribe to Explified.
Okay, thank you so much. This is an example of almost periodic phenomena. Now, let's come back to mathematics. The formal definition of almost periodic function was given in the 1920s by Harald Bohr. It said that a bounded continuous function from R to X is almost periodic if for every epsilon they correspond a relatively dense set T, such that this inequality holds for any tau in the relatively dense set T. Equivalently, a bounded continuous function is almost periodic if and only if for every sequence of real number Sn, there exists a subsequence Sn with the same notation, such that the set of translation converge uniformly in BCRX. And that condition is called the Bochner criterion. Now you see that if the function f is capital T periodic, then we replace tau by capital T, and this inequality holds true. So indeed, this shows that periodicity, periodic functions are a subset of almost periodic functions. Examples of almost periodic functions include the trigonometric polynomials. Generally speaking, if G is cosine alpha t plus cosine beta t, then G will be almost periodic if alpha over beta is not a rational number. So that means if you take two periodic functions with different periods, okay, such that the quotient is not rational, then the sum is no longer periodic, it is almost periodic. That's an example of the graph of these functions, which is almost periodic, but not periodic. It's important to notice that every almost periodic function is uniformly continuous on the real number set. Now, a concept which is very important here when we study almost periodic functions is the one of average of such functions. So if f is almost periodic with values in Banach space, let's say generally speaking, a complex Banach space X, then for any real number lambda, A defined like this exists always, that's the average, and is different from zero at most at countably many points lambda. And the set of all lambda with non-zero average is called the Bohr spectrum of F, which we denote by sigma sub B of F. And we will take this notation for the Banach space of all almost periodic functions under the sup norm. It is important to notice that it's usually difficult to write down many almost periodic functions which are not periodic. So for a long time, the question was to, know what is the amount, okay, of almost periodic functions which are not periodic. So we were able to give an answer to this important question. We proved that the set of omega periodic function is a set of first category in the space of almost periodic function. That means that the set of almost periodic functions which are not periodic is really huge. Another concept of almost periodicity is the one due to Besikovich. First of all, we consider the Marcinkiewicz space, which consists of all LP functions equipped with this norm. And if you take a function in the Marcinkiewicz space with exponent p less than infinity, then we say that it is Besikovich almost periodic if this equation holds true. And we denote by BP Rn the set of all Besikovich almost periodic functions. Finally, we present here the concept of almost automatic functions due to Bochner. Actually, Bochner was working on some differential geometry problems, and he encountered some automorphic functions on the real and complex manifolds, which has these characteristics. And he called them almost automorphic functions. So these are functions which are bounded and continuous, such that for any sequence of real number Sn prime, there exists a subsequence Sn such that this double limit is equal to f of t for each t. And equivalently, we have these two limits pointwise in t. Now, it's clear that if the limits here exist uniformly in t, we recover the almost periodic function in the sense of Bohr. It is important to notice that an almost uniform function may not be uniformly continuous, so that makes the big difference with the almost periodic functions. And here we have an example of almost uniform function, which is not almost periodic, as was given by Levitin. Here is the graph of such a function. You can find more on this class of functions in my recent book. Another example of almost ordinary function, which is not almost periodic, is the one given by Vich. It's that function here with values in the unit circle, the complex plane. Okay, this double inclusion, strict double inclusion, well known. It's we have an example that to prove that they are strictly included p omega into apx and apx into aax. We were also able to prove that the set of almost periodic function is a set of first category in the set of almost automorphic functions. That means the amount of almost automorphic functions which are not almost periodic is huge. So when we were dealing with periodic functions, it was easy to define the frequency of such functions. Now, in the case where f is not necessarily periodic, but it is just, let's say, bounded, the concept of frequency is rather complicated, and roughly speaking, it is the set of frequencies that characterize the behavior of the function, meaning that the larger is the set of frequencies, the more complicated, all right, is the shape of the functions, okay, the behavior of the functions. And for almost periodic functions, the Bose spectrum is just the set of frequencies of the function. Now, let's get to this equation, ODE, with a generator of a C0 semigroup, which is analytic. We assume that the forcing term is almost periodic, and the spectrum of A does not intersect this set. Then there exists a unique almost periodic mild solution U, whose spectrum, Bose spectrum, is a subset of this closure of the set of frequencies of F, meaning that the solution, the unique solution, actually behave at most as the forcing term of the equation. Now, all methods that were used to prove this theorem are based on the uniform continuity of the forcing term. And when we have a function, I mean, the forcing term not necessarily uniformly continuous, then this condition here, okay, is no longer sufficient to have a unique mild solution. So our aim was to generalize to almost automorphic case the previous theorem that was dealing with almost periodic forcing term. So we come up with a concept of a spectrum that we call uniform spectrum to try to tackle this problem and solve it. This is the first time actually that we have a concept of spectrum of functions from the point of view of differential equation. So far, most of the concept of a spectrum of bounded function are due to the harmonic analysis study. So in 2004, in the proceeding of AMS, Diagana, Min, and myself, we were able to introduce this concept of uniform spectrum. First of all, for a bounded continuous function, we say that a real number alpha is uniformly regular with respect to the function f, if there exists a neighborhood U of I alpha in the complex plane, such that this function has a complex function of lambda with real part of lambda not zero, this function possesses a holomorphic extension on the neighborhood U. Now, if alpha is not uniformly regular, then we say that it belongs to the set of uniform spectrum of the function f, and we denote this set by SPU of f. So with this new tool, we were able to prove theorem number 7 with this time. It's actually the same equation earlier, but this time f is almost automorphic, and we assume that the spectrum of A does not intersect this set. In this case, we were able to prove that that equation 2 has a unique almost automorphic mass solution W, such that the uniform spectrum of W is a subset of the uniform spectrum of the forcing term F. This is indeed an extension of the theorem number 6 for 2 reasons. One is that if F is uniformly continuous, then the Kalman spectrum coincides with this uniform spectrum of F. And if F is almost periodic, then we have these 3 sets that are the same. So indeed, we see that theorem 7 is effectively the generalization of the theorem number 6. So we were able to solve the problem. In this book, you will find all information about the concept of spectrum of bounded functions from harmonic analysis as well as ordinary differential equations. Now, finally, we have this, what we want to do actually to end this talk, we would like to study the pendulum almost periodically first. But first of all, we look at the general framework. We consider the second order elliptic equations, which is here. We formulate 4 assumptions. One is this condition here for regularity, okay, coefficient. Assumption number 2, we assume that C of x, okay, is away from 0. And number 3, the assumption, we assume that all coefficients of the equation belong to the space of almost periodic function, which satisfy a uniform Holder condition with exponent alpha, when alpha is between 0 and 1, if n equals 1, and alpha between 0 and 1 if n is equal to 1. The final assumption is the Lipschitz type conditions on the right-hand side of the equation. We have these 2 conditions here. So with this in mind, we recall that a super solution of the equation is a function u sub bar here that satisfies this, and u is a sub-solution if it satisfies this inequality. So we assuming that there exists a pair of sub and super solution to our equation, and we assume also the 4 assumptions to be true. Then for any S in the Bohr compactification of Rn, okay, there exists a solution, okay, which is in BC2 plus alpha, exponent 2 plus alpha of equation number 2, which is between the sub-solution and the super solution in the envelope of the equations. Furthermore, there exists a residual set omega sub AA in the Bord compactification of Rn and a set of measure 1 omega sub B in the Bord compactification of Rn, and both sets are translation invariant, said that US will be uniformly almost automorphic if S is in this first set, and it is Besikovich almost periodic if S is in the other set, omega sub B, subset of the Bord compactification of I. How do you prove this? We actually use the method of sub and super solution. And as you know, this is a powerful method used to, in the case of boundary value problems with periodic coefficients, that the first time was introduced by Peano and Perron. And then naturally, we expected this to be extended to almost periodic case. Now, the method actually does not have a direct extension to almost periodic elliptic equation. So what we have done here is to combine this method with the Bord compactification of the Euclidean space, basically because of that space is metrizable. And we combine also with the method of monotone operators. And a very important fact here is the fact that for any almost periodic functions, there exists a unique continuous functions, okay, on the Bord compactification of Rn, okay, that correspond to that function. So that's also a very important result that we use to obtain the result here. Now, as you can see, we have not, I'm sorry, let me get back here. As you can see, there is no almost periodic solutions, although all the in condition H number 3, we assume that all coefficients are almost periodic in the sense of Bord. So if, in addition to the assumption of theorem number 8, we assume that C of X is greater or equal to 0, and these inequalities are satisfied, and C is uniformly continuous on this strip here, okay? I'm sorry, G is uniformly continuous on this strip here, then our original equation has a unique solution, which this time is almost periodic and satisfy a uniform Holder condition of exponent 2 plus alpha. And of course, that solution is between the sub-solution and the upper solution that we assume in theorem number 8. We apply this to study the pendulum almost periodically forced. The equations in the envelope is written like this, and we let gamma to be the modulus of H. Now, we have two conditions. First of all, if the norm of H is equal to A, then for any S in the Bord compactification of the real number set, we have a solution which is C2, bounded and continuous C2, which is between pi over 2 and 3 pi over 2, okay? And furthermore, we have this condition here, which is exactly the, the application of theorem number 8. Now, why we have this? Because actually the main assumption is that there exists a pair of sub and super solution, and in fact, you can check that pi over 2 and 3 pi over 2 are respectively the sub and super solution of the pendulum equation. In the case of the norm of A is strictly than A, then this time, again, from these corollary that we have earlier, we have a unique solution which is almost periodic, okay? And in between these two, of course, again here we have a sub solution and a super solution. So in conclusion, we say that periodicity is everywhere and every day, of course. Everybody is concerned with periodicity. You know the case of biological clock. There are several types of periodicity. Almost periodic functions and almost automorphic functions exist in plenitude. Periodic and almost periodic ODE and PDE may not possess almost periodic functions. And in studying such equation, one must consider almost periodicity at large. So I thank you very much for your attention. Thank you.
The question is, can the Mesfer theorem for periodic equations be extended in an infinite dimensional space and for more general classes of functions?
Okay, I think this is a very interesting question. Let's say, if you go to the proof of the original Masira theorem for periodic equations, we actually turn the problem into a fixed point theorem for the Poincaré map. And this works only for the forcing term being periodic. So even in finite dimensional space, if the forcing term is no longer periodic, but let's say almost periodic or almost automorphic, then this method does not hold anymore. One way to solve this, I think we did it, was to actually use the Floki theory. The fact that we can, let's say, the operator A of t does not depend on t. That's the Floki theorem. And then we can go further to say that the operator A is of the Jordan canonical form. Even if you can say that it's one form. In this case, we consider the solution as a vector, okay? We look at the last coordinate, the nth one. We can prove that that coordinate is almost periodic or almost automorphic based on the result that we know on primitive of such functions. Then we go to the n-1 coordinates up to x1. This method is called method of reduction. Basically, we reduce a problem in n-dimensional space into a one-dimensional space. That's a method that I introduced in 2001 in my book that Professor Goldstein mentioned earlier.